I forget to push the go button, it doesn't work. All right, so let's get started. I apologize that the video is a little wonk. It's a little tilted, but that's all right. Star formation is isotropic, so it doesn't really care which direction it's going. So today, we're going to talk about the formation of stars. So we've talked about the lifetimes of stars and their deaths, and now we're going to talk about their births. And so I'm going to spend today talking about kind of core physics ideas around star formation, and then Wednesday we'll talk about more things and clean up a bunch of ideas. Everything that's on, why are you streaming? Everything that's on the homework will show up today. So you should be able to do the homework. Okay, and other things. Grades, please take a look at your grade on Canvas. I think that everything is right, modulo a couple of typos, so there might be a couple typos in there. I'm going to go through it again carefully after class, but I just went through it and I put zeros in for everything that people are actually missing and put actual grades in where they were missing, and graded all the things that were outstanding. So now your grade on Canvas should be relatively accurate. Yeah.
Apparently you didn't put a submission button for the last two readings.
Oh, fart! That's why nobody did it.
Oh, yeah, I emailed you about that. Or like
I tried to submit it this morning.
Yeah, okay. I haven't. Yeah. I noticed nobody had done it, and then I was like, I don't really super care. I'm gonna move on. So I'll put a submission. I'll put the submit button. It's just there's a way to make assignments on Canvas by just pushing a button, and so I filled in the thing, but it doesn't have an option on that little quickie thing to make the submit. So anyway, sorry about that. I'll fix that. Again, low priority. If you get it, that's fantastic.
What is it? The readings altogether are 5% or 2%?
5%.
5%.
5%. But really, they're graded in the easiest way possible. So as long as there's something there, you get credit. So if you're missing readings or numerical homeworks, the grading for those are really, really easy. Don't leave those points on the table.
So if we went back and did the ones that you put in as zeros, like you would be like, oh, he submitted something, and then change it, or?
Yeah.
Okay. No,
I mean, it should say something sensible. Don't just.
Yeah, no.
So,
but
Asking for a friend.
Right.
Yeah, not me, of course.
For instance, I happen to know how everybody's doing. Okay, so anyway, and if there's something, I make typos like it's my job. So if there's a typo, please check the math and check against the grade that you think you got. Okay, so now we're going to talk about star formation, and I'm going to write down the things that we're going to do over here so that I remember to do them in order. This is some of my favorite stuff, and I'm going to jump right into the physics. And I'll have all of the great pictures that go along with star formation on Wednesday. So star formation is responsible for a lot of best images that Hubble produces. These star-forming regions are incredibly beautiful objects. So I'll show you pictures of that on Wednesday. But right now I'm going to talk about physics. So we're going to talk about what happens if you just let something collapse. We're going to talk about the gene's mass and also the gene's length, which is a hilarious thing to have to Google when you want to Google the gene's length. It does come up. It's just not the first hit anymore. It used to be the first hit, but now it's legalized.
And
James' genes.
Is that the same genes as the Rayleigh genes?
Yeah.
Cool.
James' genes has his name on a bunch of stuff. And then we'll talk about the star formation rate. And then we'll talk about the initial mass function. And I already did talk about the initial mass function way back when we talked about distributions, but I'm going to talk about it again because it's important. So, here we go. Okay, so I have a cloud of gas. It has a mass, m, and a size L. How long does it take to collapse? we can sort that out using, you're going to sort it out on class, do it in the homework using my favorite way to do it, dimensional analysis, which gets you most of the right answer really easy without thinking very hard. To get the remaining factor of square root of 3 pi over 32, which, how big is that actually? Does anybody have a calculator faster than me? What's this? Yeah. Sorry, it's 3 times, this is a number that I should know off the top of my head, but
It's like a little less than 1/3.
Is it 32 in the square root?
yeah, everything's in the square root.
Oh, everything's square rooted?
Yeah, that's like a half. So it's like a factor of 2. So there's a bunch of work for a factor of 2. Or the dimensional analysis, which is just, you just write down the answer and you get basically the right answer. So I'm going to show you the long way. So we've got 2 big derivations. We've got the free fall time, not a big derivation. We've got the Jeans mass. The way I'm going to do it here is not a hard derivation either. Doing the Jeans mass properly, we'll have to wait for hydrodynamics in the fall because we have to perturb the hydrodynamical system, and that's a little bit harder, and we haven't done that yet. So I'll show you the cheesy derivation of the Jeans mass, which actually, again, works to within a factor of 2. And then we'll talk about the star formation rate and the initial mass function. So that is the mass distribution of stuff after it forms. Okay, so first, I have a cloud of gas with a mass m and a size L. How long does it take to collapse? Well, let's sort that out. This isn't something that I expect you to have known. That was a rhetorical question. So let us say that my mass is a sphere, because we always make things spheres because it's so much easier. Spheres and cubes. And it has some length. Let's call our length r for radius. Right. So I'm going to think about what a little test molecule at the edge of this sphere is. So this sphere has a density, rho equals 4/3 pi, m over 4/3 pi r cubed. Right, so the volume is 4/3 pi r cubed, and the mass is m, so the density is m over 4/3 pi r cubed. And because this is a sphere, I can pretend that all of the mass is located at a point at the center, because it's spherically symmetric. We did this derivation, but it's confusing and it went by really fast because I didn't spend a lot of time on it. But it's a relatively, once you've done it a couple of times, it's not too painful a derivation. But you can show that if it's spherically symmetric, then all of the mass, you can just pretend it's at the center. So then what do I do? Then I say, okay, what I want is I want to know how long it takes for this point to fall towards the center. So I'm going to make this look like Kepler's problem with an eccentricity of 1. So this is now an ellipse with an eccentricity of 1. So what does that mean? So let's talk about what an ellipse looks like. So an ellipse looks like this. Here's my foci. Here's my center. This is AE. This is A. I'm going to do this the long way because when I sat down to do this derivation getting ready for class, I was off by a factor of 2. And I'm like, what the hell? Why am I off by a factor of 2? It just took me a minute because I've been doing this for a very long time. So how I screwed this up was a little surprising. So if I have an eccentricity of 1, what does that mean? That means it's very long and skinny. That means it's a line. And that also means that the focus is at the edge. So the focus, so an orbit with an eccentricity of 1 looks like this. Does that make sense? So my 2 foci are the black dots, and my mass is going to be concentrated at 1 of them. So now I've got an orbit problem. So what does this orbit problem look like? Make sure I got everything in. So what does this orbit problem look like? So my test molecule is going to start off here. It's going to accelerate here, hook around, and come back. It has 0 velocity here and a lot of velocity here. So we're going to use Kepler's law. And we're going to say that period squared equals 4 pi squared a cubed over g times m. Okay, I don't want to deal with a cloud of mass m. I want to deal with a cloud of density rho. Because it turns out the mass doesn't matter, only the density. The mass disappears. Or I'm going to get rid of it, whichever. So the intrinsic density, which is the intrinsic quantity, not the extrinsic quantity, is the only thing that this depends on. So let's get rid of everything but the density in this. So I've got an m and an a cubed. This is like 1 over density, right? So let's talk about how these things line up with this cartoon problem that I've got. So I can see that it's going to turn into the density. Cool. So period squared is going to go like 1 over the density. I can tell that just by the equation. But let's interpret this for a second. So what's A?
Half the distance.
Semi-major axis.
It's the semi-major axis.
So half of the path?
So on here, where is A? A.
It's this from the center to one of the points.
From the center to the end. And the end is the focus here because of the eccentricity is 1. So A is r over 2. And I don't actually want p because p is the time it takes for the molecule to start here, hook around the star, and then come back here. I want to know when everything is going to pancake to the center. Everything is going towards the center. Everything is going to hit each other in the center. It's a sphere. Everything's going towards the center, and it's all going to splat at the center. And then it'll overshoot and do other things. And then there's violent relaxation, which we'll talk about at xscale.
Violent relaxation?
It's one of my favorite things. We'll talk about it at xscale. So this thing collapses to a point, and we're just going to stop it at the center. So what I want is the free fall time, which is going to be the period over 2, because I just need half of it. Does that make sense? Do you see okay? And A is going to be r over 2. Is going to be r over 2. Is that right? Yes. So let's plug this in. I'm left with t free fall. This is 2t free fall squared equals 4 pi squared r cubed over gm times 1 over 2 to the 2 cubed. That one's cubed. So this 2 came from my 1/2. Now, this is just a little bit of algebra. I'm just going to plug this in here, and I'm left with the free fall time equals, this is going to be a 4, so that's going to cancel out this 4. Pi squared, and then the r and the m cubed, let's take care of those. I got a g, I got a 4/3 pi rho, that's the m, r cubed. So my r cubes cancel. So I just have a 4/3 pi rho, and then a 1 over 2 cubed. What's 2 cubed? 8. What's 4 times 8? 32. So this 3 goes up to the top. No worries. So I get 3 pi over 32 g rho is the free fall time squared. So the free fall time, I'll leave that there. We're going to call this t free fall equals 3 pi pretty much over 32 g rho, square root of that. Okay, the important bit is the 1 over square root of rho. So the time scale for a blob of density rho to collapse is 1 over the square root of rho. And the g is in there just to make the units make sense. That all make sense? So this free fall time determines how long a cloud will collapse. So there's this really cool, how many of you can find the Orion constellation?
Yeah.
What's that?
Yeah.
Yeah, so not right now, is it?
It's down there over right now.
So it's a little hard to see because the planet's in the way. But it'll show up in the, where am I? Over there, sorry. I got to point at the right part of the sky. It'll show up over there tonight, I think. I think it's up now. So
Yeah,
you can see it.
around 8 p.m.
Right, so it'll show up, so Orion has 3 big stars, Minac, Alcanac, and Alunam, which we learned about, right? And then it has 3 stars of his sword. This middle star isn't a star. This is called M42. And it's a star-forming complex. It's a nursery of thousands and thousands of little baby stars being born as we speak. And there's this huge cloud of gas at M42 that surrounds all the stuff. And if we say, okay, this thing is forming stars, it has baby stars in it. How old are the baby stars that are in it? They are 10 million years old. Okay, so that gives us one benchmark. What is the free fall time for the cloud? It is 3 million years, which is problematic because if the cloud's supposed to collapse in 3 million years, but there's shit in it that's 10 million years old, there's something wrong with this free fall time, right? So the free fall time is right. It's that there's other physics that I've neglected that I will hint at, but not actually get too deep into the weeds. The free fall time is just if it goes straight down to the bottom. But things don't actually do that. It's turbulent and violent. So why the star formation rate isn't higher is an interesting question. We'll talk about that for a second. So given a cloud of mass m and size L, now I do need m and L. Now it is an extrinsic quantity. How many stars is it going to form? Well, we need to sort out what the unstable mass is. So I'm going to erase all this. Now we're going to go hit up the gene's ass. So I'm going to say I got a sphere. Everything's a sphere right now because it's easy. What is the time scale? So if I have this cloud of gas, I should have brought a picture. It would have been good. Imagine the pillars of creation if you can imagine that image, the fingers. That one looks too much like a middle finger. There's this, anyway, sorry. So if I have this cloud of gas, how long does it take for a sound wave to cross this cloud? We're going to call this L. Sound waves propagate at the speed of sound, which is gamma p over rho. It's also kt over f. We'll put a tilde there because sometimes there's a 3/2. So the sound speed is roughly the thermal speed. So kt is the thermal speed, right? Oops. 1/2. Kt is an energy. You need a half. So sound waves propagate at the speed of sound. Pressure waves propagate as sound waves at the speed of sound. So if I squeeze a little bit of this cloud, make it a little bit denser, the pressure is going to go up and push against it, and a pressure wave will be launched through that thing and will equilibrate the density. So how long does it take if a pressure wave travels at c sound? What is the crossing time for this cloud of length L?
L squared m over kt.
Simpler. Think dumber.
L divided by the speed of sound.
Yeah. L over c.
What did I say?
Just L over the speed of sound. It's just
Wait, C is sound. Oh,
C
I
sound,
see,
yeah.
I see.
yeah, I forget what I'm doing sometimes, and c is the speed that's relevant. So for the moment, it's sound. So the crossing time is the length over the sound speed. So what I need, when I have one of these clouds, it's basically being held up by gas pressure. Okay, not really. I'll tell you more about that later. It's basically held up by gas pressure. So I've got these two competing forces, gravity pulling in and pressure pushing out. And we saw that in the force balance equation, right? It's the competition between gravity and pressure. So if the crossing time, so if I have a disturbance and I squeeze it, and the pressure crossing time is long compared to the free fall time, so if T cross, if it's going to take longer for the thing to equilibrate its density than it is for it to just collapse to a point, what's going to happen? It's going to actually collapse. So if the crossing time is bigger than the free fall time, you have an unstable situation and it will collapse. So let's figure out what the biggest crossing time is. So bigger things have longer crossing times, so will be harder to support. They're also more massive, so they are harder to support. But let's just think about lengths for a second. So I say T cross is bigger than T free fall. That says that L over the speed of sound has got to be equal to, let's just call this 1 over, let's drop the 3 pi and the 32 for now. 1 over g rho. So the length is just L has got to be bigger than L over, C over square root of g rho. So if the length is bigger than C over the square root of g rho, that's unstable. This is defined as the Jeans length. And there's factors of 1 in there, but what I care about is C and 32 pi. So let's write the Jeans length. Is C over g rho. So this is how big a thing is. And then I could turn that into a mass. So my cloud has a density rho. How do I make a mass out of a length and a density? Which is 4/3 pi r cubed. I don't think I needed to erase all of that. So the Jeans length goes like C over square root of g rho. So the Jeans mass is going to be 4/3 pi times rho times L cubed, which is just going to be 4/3 pi. I'm going to put these 4/3 pi in quotes because I'm being sloppy by factors of pi. There will be slightly different factors of pi when we do it properly, but I'm not worried about that. And then rho times L cubed. L cubed is C sound cubed over g to the 3/2, and then rho, I got rho to the 3/2 because I cubed this, and then I just get a rho to the 1/2 because I got that other rho. So the Jeans mass is the sound speed cubed over g to the 3/2 rho to the 1/2. I'll put a little tilde there. I'll put a tilde here too, because those are approximate. But that captures the physics that's important. The physics that is important is gravity and density and the sound speed. Sound speed is what's supporting the cloud. Density is what's trying to make it collapse. So if I have a cloud that has 50,000 solar masses, but it's got a Jeans mass of 100 solar masses, how many stars is it going to make? Make whatever 50 divided by 100, 50,000 divided by 100 it is, it'll make 5,000 100 solar mass stars, or thereabouts. Yeah.
What order of speed are we talking about when we're talking about sound speed in these things?
On the order of several kilometers per second. So in a molecular cloud, so that's a good question, and that's actually should be a homework problem, but I didn't put it there. So the sound speed for 10 Kelvin gas is 0.2 kilometers per second. And 10 Kelvin is cold. Yeah.
So we define L as the diameter. So wouldn't there be like a factor of 1/8 in there when you put in volume?
Yeah, I'm being sloppy by a factor
Okay.
too.
All right, but it should be like 1/2
If
L.
you're being careful, there's factors of pi's and stuff that you need to be careful of. But if I just say L is the radius, that's fine.
Okay.
Like this is here we're off by a factor of 2 one way or the other.
Does the sound speed depend on density as well?
No.
No.
Does it depend
No,
on
sound speed.
temperature?
Sound speed is gamma p over rho. Sound speed squared is gamma p over rho. I said that wrong on the board earlier. Which equals to kT over mass of the particle, or better, but let's write it this way, mu, which is the chemical concentration, or the chemical composition, times the mass of the proton. So the sound speed nominally depends on density, but only by way of pressure, so it only depends on temperature for an ideal gas. For a non-ideal gas, it will depend on other things. It depends on temperature and composition, so it's the weight of the particle. So weirdly, this is about the sound speed in air on Earth too, even though the temperature is 300 Kelvin higher. What's different about air versus molecular hydrogen that makes up these things? It's now more massive because what's air made out of is N2 for the most part. Air is nitrogen.
But wouldn't we expect it to be faster than 0.3 kilometers per second?
Which?
The 10 Kelvin. Oh wait, no, 10 Kelvin is 10 Kelvin.
Yeah.
I was thinking 10,000 Kelvin. I don't know why.
Oh yeah, yeah. So if I crank this up to 10,000 Kelvin, then that's going to go up by a factor of 1,000, and so the sound speed goes up by the factor of a square root of 1,000. So that's like 30. Okay. So it'd be like 60. Yeah.
Just to clarify, I know like we're not carrying with factors of 2 and stuff, and we're being sloppy, but the L is the gene's length goes for if that's the radius or the diameter, like crossing the whole.
Let's call it the radius for now, because the rest of the mass works out that way.
Okay.
But don't get too hung up on it. Call it the diameter when you need it to be the diameter. This is we're waving our hands here.
Okay.
So don't get too hung up over whether the gene's length is the radius of the diameter, because the mass is really what matters. And there's a factor of pi that I'm missing out of that. So I'll do a better derivation of the gene's mass later and show you where all the actual pi's ought to be.
Gotcha.
And then it becomes the diameter. Okay. So if mass of the cloud is 50,000 solar masses, and I sort out that the gene's mass is, let's say, 5 solar masses, then I'll have 10,000 stars that can form out of that. Because that's about how big a star is going to be. Now, this is not actually accurate. I've got to do something a little bit different. So let's talk about the mass distribution real quick. And then we'll talk about the star formation rate. How am I out of time? Doing okay. Oh, I've got 15 minutes. How do I strategize? So let's talk about the initial mass function real quick. So how many of what mass do I form? So there's this function. Actually, I'm not going to call it that. Some people call it phi, and I hate that. The initial mass function we call it dn dm. The reason that I write it like a derivative is because it's explicit about how I'm doing the counting. I could have dn d log m as well, and I get a different number that way. And people do that in the literature a lot. I'm going to keep it simple and just call it dn dm. This is how many stars I have in a little mass bin. This, let's be explicit, is some number times the mass to the minus 3.5. Is a power law. So if I have 10 stars at 1 solar mass, how many stars do I have at 2 solar masses? What's that?
20? Oh, not 20.
It's negative, so it goes down. So what's 2 to the 3? 8. So 2 to the 3.5 is like 10. So I'll have like 1.
Yeah.
Right. So I'll have like two solar mass stars.
Um,
It's a pretty steep function, huh? So how many 4 solar mass stars am I going to have? None. Because I can't get this any smaller. I can't have a half of a 4 solar mass star. That doesn't make any sense. So let's say I have 10,000 of these, then I'm going to have half as many 2 solar mass stars. But it goes down like to the power to the third. So this is a very, very steep function. That means we don't have very many massive stars. So 100 solar mass stars are incredibly rare because they fall off like this. And it peaks at about a half a solar mass. And this is a little nebulous. So the function dn dm looks kind of like this. There's some curvature, and clearly it doesn't keep going up forever. We don't have an infinite number of 0 mass stars. That doesn't make any sense. So it rolls over somewhere around a half a solar mass. But the power law starts shortly thereafter. So it's a good power law up until a long way. So one of the reasons that we need to know about this is, say I want to know what the luminosity of a star cluster is. The luminosity goes like the solar luminosity times the mass is solar masses to the also 3.5. This is plus 3.5.
It's a 3.5 outside.
Oh, man, stupid squirrels. 2.35, not 3.5. 2.35. That exponent should be 2.35, not minus 3.5. Fix all your notes. That's why I had a 3.5. The squirrel left it on the table. The 3.5 goes here. I was writing the homework recently. So luminosity goes like mass to the 3.5. Bigger stars have more light by a lot because they're hotter. So if I want to know what the total luminosity is, I'm going to integrate from the lowest mass to the highest mass. I can't integrate this to 0 because this blows up at 0. It doesn't make any sense. So we're going to set a lower limit of like 0.07 solar masses. And I don't know what happens above 100 solar masses, but there's nothing up there, so we'll just say that my top is 100. Maybe I'll say 150. I'm going to be squishy with that in the problem. So I've got some lowest mass to some highest mass. And then I've got the luminosity, which is a function of mass. And then I have the distribution, dn, dm, dm. And I integrate this over mass. And that gives me luminosity, because the luminosity I have is a function of mass. So I plug this in here, and I get m to the 3.5 times m to the minus 2.5, and I do that integral. I'm not going to go through it because it's a homework problem, and it's something that I want everybody to work their head around. So I'm going to erase all that and just say that one more time. The initial mass function is a distribution. And whenever I have a distribution, I can integrate q of h times the distribution f of h dh to get the total q, if q is a function of h. So if I'm looking at luminosity, I'm going to say the total luminosity is going to be the luminosity as a function of mass times the distribution, which is a function of mass, and we integrate over mass. This has got to be inside the integral when you do this integral. Otherwise, you get the wrong answer. Does that make sense? If you want the total mass, what do? You integrate the mass times dn dm, and then you integrate that over dm. So here q is just mass, so that's just by itself. If I want the total number, then I just integrate the distribution itself. This counts them, this weighs it, and this tells me how bright it is. If I want some other function, I can cram another function in here, whatever other functions that I want. All right, last thing I wanted, does that make sense?
Yeah. Do the DMs cancel out? Or is that just
Um,
a function?
Ish in a hand wavy way, but this dn dm, I mean, yeah, as a physicist, yes, they cancel out. Because I'm going to write dn equals dn dm dm. So I can do that. So they cancel out. I just have to be careful. You can't do then an integral over n without changing this. So
Right.
yes, they do, but don't without getting
So
the
this is
Jacobian
okay if you're a physicist, but it would make a mathematician scream.
to do that.
Yeah, okay.
That's how we roll. So yeah, kind of, but no, don't.
But no, don't.
Yeah, I mean not really. So they cancel in squishy ways, but I wouldn't actually do math that way.
Darn.
Because dn dm isn't going to have a dm in it when you plug it in. When you plug it in, it's going to have m to the minus 2.35.
So does that end up being like a double integral?
No, it's just one integral.
Just one.
So I say that if I want the total m, then that's going to be m times dn dm dm from my lowest limit, which we'll say for now is 0.07, and we'll call this 103. Totally random. So if I want to do this, then I need to know, then I plug in here. This gives me low to high. M times n naught m to the minus 3.5 dm. And you got to do this integral. N naught is a number that I will help you figure out in the problem. That's the total number of, that's going to be related to the total number of stars.
And that's
Oh, sorry.
Go ahead.
Go. You go.
That's where the 2 point something comes from.
Jesus Christ. 2.35. That's what I get when I'm talking and writing at the same time. Yeah.
Clarifying question. dn over dm, that's some function of, it's like a derivative of some function of n of m.
I am determined to write this number wrong all day. Don't think about it as a derivative, think about it as a distribution. Don't think about it like a derivative. I'm just calling it this because that's how I'm going to do it, is I'm going to count up all my n's and I'm going to divide by m's. But it's not really a derivative of anything. Does that make sense?
So it's how many stars are in that mass range?
Yeah. So I have my mass. We're going to call this dn dm. I'm going to break space into a whole bunch of tiny little bins. Each one of these is called dm. It's dm1. It's formally infinitely small, but I'm going to draw it finite because I can't draw infinitely small. So dn dm is just how many n. It gets a d because it's infinitely small. How many n are in this column? Does that make sense?
Yeah.
And since it's infinitely small, its area is actually 0, so there's actually 0 things
So
here.
does it normalize to like a 1, like a distribution? Or does it like actually have numbers of stars per mass?
This one, the way I've written it, normalizes to the total mass of the system.
Okay.
So that's an important question, is how does this distribution normalize? So I always talked about distributions needing to add up to 1. This one doesn't quite. You have to get it to add up to 1, but that's just dividing by the total. It's very easy. Okay, and the last thing, yeah, I got 5 minutes. I'm going to stand here for a second. Does anybody have any questions about the IMF? Because the next bit is also confusing. So, okay, so cool.
Yay.
I'm cramming all the confusing things into one lecture.
Wait, this was semester?
All the confusing things about star formation, no, that's not true. It gets so much worse. So what we need to do next is measure the star formation rate. So we talked about the mass distribution, and here with my initial mass function, we'll write dn dm equals n naught m to the minus 2.35. And the star formation rate, okay, write this down. I'll write it up here so that it's really. because I don't know if this is in the book. Oh, there aren't any homework questions on it though. But anyway, usually there's a homework question on this, but I forgot to put it in the homework. The star formation rate is the H alpha luminosity of an object. So if I have a star forming complex, I measure the H alpha luminosity. And then the star formation rate is H alpha luminosity divided by 1.26 times 10 to the 41 ergs per second.
That's Lyman alpha hydrogen, right?
Yes, it's hydrogen alpha, yeah.
Okay.
So yes, Lyman.
That's the luminosity of the Lyman alpha
Yeah.
transition of hydrogen.
Yeah, so you measure all the Lyman alpha photons, you divide by this number, and that gives you the star formation rate in solar masses per year. So I'm going to spend 3 very confusing minutes trying to explain where this number comes from. Since I haven't turned it into a homework problem, one of the things that I've always wanted to do but never sat down to do is turn this into a homework problem for class, but I haven't done that yet. So that is the correct answer. So how do I measure the Lyman alpha flux, and why is it related to the star formation rate? It's related to the star formation rate because it is the formation rate of massive stars, but not directly. It's this very indirect measurement. So if I want to measure the star formation rate of a galaxy, I can do it pretty easily just with that, but interpreting it is a little tricky. So let's talk about what happens. So I have a cloud of gas. These clouds that stars form from are very cold. They're like 10 Kelvin. Why are they 10 Kelvin? They're 10 Kelvin because they radiate like crazy. And they're optically thin. So there's no opacity, and they radiate, so they cool. So they get down to 10 Kelvin pretty easily. Now, when I have a little knot, if I have a Jeans mass of this cloud, which remember is set by the density and temperature, if I have a Jeans mass that turns into a star, that might be a massive star. And if it's a massive star, then it's going to spit out a whole bunch of UV photons. Massive stars make UV photons in lavish abundance. What do UV photons do to hydrogen?
Excited.
What else do they do? They do more than that.
Ionize?
They ionize it because they're UV. They're short, right? So they're short enough to ionize. So H1 turns into H2. And actually, we start off with a cloud of molecular hydrogen, H little 2, and then that gets formed into H1, and then that forms into Roman numeral 2. This is ionized.
What's the difference between that 2 and the other 2?
This is molecular. So this means 2 hydrogen atoms
Okay.
made of 2. This is a chemical formula, just like you're used to from chemistry. This is spectroscopist's notation, which is this annoying thing where 1 is the ground state and 2 means you've got an electron removed.
Okay.
So here we've removed the electrons.
So
Yeah.
why does the molecular hydrogen, why does it become H1 spectroscopy notation? Why does it become atomic hydrogen?
UV photons.
Oh,
They break everything up.
And
it's-
ionize them.
And really, it's not even, it's kind of a complicated dance how it turns into H1. It collisionally dissociates, but let's blame it on the UV photons for now. Because they will also do that, yeah.
So H2 is diatomic. Is H Roman numeral 2 diatomic?
I don't think you can do that.
I don't know.
No, it's atomic. It's atomic.
It's atomic?
Because it's ionized. You don't form. You never have molecules if you have a substantial ionization fraction, because it's usually too hot to break such molecules.
Okay.
Careful with that, never. But I'll stand by it for now. Okay, we're not done yet. So we ionize these. We make this H2 region. So now we have an H2 region. So here's my little star. Oh, well, let's make it blue because it's an O star. Here's my little O star. Is there a pink one? Sweet. Because H2 is actually pink. I get this region of H2 around it. H2 doesn't make H alpha, but it will once the H2 recombines. And then it makes H alpha. And this I can measure. I can measure other things too. But I measure this as the end point of this cascading process to know how many things I did here. So I have the number of massive stars times the number of photons per massive star times the recombination rate to H1. So it's the number of massive stars times the photon production rate for each massive star times how fast it actually makes an H1 photon. You don't need to know this part. I'm just telling you so that you have heard it. So this is the H alpha luminosity. So we get the H alpha luminosity, and then this is a thing I can sort out, this is a thing I can sort out. So the only free parameter is the number of massive stars. This gives me the number of massive stars. But I want a rate. How do I get a rate from a number?
Divide.
By? What kind of thing do you got to divide by?
What you're comparing it to.
Well, if I want a rate, if I want gallons per second.
Time.
Time, there you go. So we've got to divide by a time scale, and we know pretty well how long massive stars live. So this gives me the H alpha flux, and then we divide by the massive lifetime. The reason that we use massive stars as tracers for star formation is, one, they're really violent objects, so they really leave a really substantial mark. And two, they only live for like 1 million years. So when I want a time derivative, I need dm over dt, and m's got to be little and t's got to be little. That's how a derivative works, right? So if t is little because the massive stars don't live very long, why is m little? From the IMF, we don't have very many massive stars in the first place. So both of these are little numbers, and so I can make a reasonable derivative out of them. Okay, is that everything? Yeah.
When you said recombines, what is it recombining to? H2 gas?
The H2 recombines to H1.
So it just falls down?
Yeah.
in energy?
Yeah, so it looks kind of like this. So I have my massive star here, and it burns an H2 region around it. And then out here, I need a third color. Out here, it starts to recombine. So close to the star, it's H2, but there's a wind coming off of this stuff. So once the ions get out here, then they can recombine to form neutral hydrogen again.
So it just collides with other neutral hydrogen and like transfers all the energy to like fall back down?
Yeah, it cools. Once it's away enough, then it'll cool, and if it can't see enough UV photons, then it'll fall back down.
Okay.
Or there's a free electron there that it'll catch, and then it'll fall back down. Okay. Does anybody have any questions about this one?
So the ionized hydrogen just catches electrons, becomes H1 again, and then
You see it, and then it'll do some other stuff.
but that's the luminosity we see, and then
That's the luminosity we see.
we divide that luminosity by the massive lifetime.
The lifetime of massive star. Well, no, you don't have to do that. That's already been done to get this number here. So this 1.26 times 10 to the 41 is the result of stellar evolution, the IMF, and some atomic physics. So it's kind of gnarly. But the end result is just you divide by this number. It's kind of nice.
So we don't divide that by the massive lifetime. We get that and divide it by 1.26.
Yeah, I divide all of this crap
Yeah.
by the lifetime. And that crap has this atomic physics in it that I don't know. And somebody did that already. The only thing in this business that we don't know is the number of massive stars.
Okay.
Does that make sense?
Yeah.
The thing that you really need to know is the star formation rate. It's measured. There's more than one way to measure it, but this is the really common one that Rob Panica cooked up. 1.26 times 10 to the 41 erg per second. Okay.
And that is that Lyman alpha hydrogen luminosity is found by that?
Yeah, that's this. That's what comes out of this process. So out of this process, there's a lot of Lyman alpha photons that I get from around here.
Yeah. And so we find that.
Yeah, I
And then
measure
divide
that.
by-
I measure that. I divide by the lifetime. I divide by the number of photons per UV star. I divide by the recombination time scale, which we don't need to worry too much about.
Okay.
All right. Any other questions for today? Yeah.
What's that last thing on the luminosity?
Where?
Third.
Recombination rate.
Let's say
Oh, this recombine to H1. So this bit you don't really need to worry about. I'm not going to ask anything about this. It's just, I'm just closing all the
So what would a
gaps.
question like this kind of be?
I mean, the questions that I would ask for here are, I have a H alpha luminosity of X, what's the star formation rate?
And you just divide by.
Okay, you should divide that out.
Okay, cool.
So, yeah, I'm not going to cook up any harder problems than that for this.
And this is all the stuff that's on the homework, so we could like
All this
theoretically,
fun homework.
we could
Everything.
theoretically do the homework today and have everything we need.
Yes, you can do everything. Everything is in the homework now. I've covered everything in the homework.